counter, so this is 0. And then the basic variables, and the basic variables I am going to put as components of a vector. So I'm using vector notation. So X is a vector that has the decision variables. All of them are basic variables, all of them. And since they form a vector of basic variables, then I'm going to use the subscript capital B to remind everybody that this is basic. So it's the initial basic vector, if you will. And since it's the initial one, then I put a super zero there. So X sub B super zero, it means the vector of the initial basic variables. Everything is simple. What you need to do is to have things clearly in your mind. I'm telling you this. This is true in everywhere. If everything is clear in your mind, then it comes out of your mouth very, very easily. If something is not clear in your mind, it's very difficult to get it out of your mouth in a way that will be smooth. Okay, then let's move to the column for xj. See, I have, of course, in the top row, I have a minus c sub j, but then underneath, as part of the yellow columns, in the yellow rectangle, then I have a sub j. So a sub j is the vector of coefficients for that variable. Vector of coefficients. Coefficients where? In the constraints. A variable has coefficients in the objective function, that's minus cj, and then all the other coefficients are in the constraints. Then we have, after the yellow rectangle, then you have an identity matrix. I call it small identity matrix, and the one I call large identity matrix, small and large. And then the right-hand sides. And the number of rows is always m, because you have m constraints. So that's the notation for there. And at any other iteration, then I want to show you the following things. Any other iteration, we have this. Okay, then the first I have any, you can see the last y of any. Then more to the point, you have now the vector of basic variables x sub b. And we use capital B. It is customary to have vectors and matrices represented by bold-faced letters, capital bold-faced letter, or lowercase bold-faced letters. So in this case, x sub b is bold-faced. Okay, then if you look at the top, where I had minus cj in any iteration, now I have zj minus cj, and that's come from the algebra of the simplex method. In the algebra of the simplex method, with the cj minus zj. See, we are writing here the equations of the objective function as an equation, z minus c1x1 minus c2x2 and so on equal to 0. Then in here is going to be zj minus cj. And zj is the same thing as before, is the profit given up. And C sub j is the contribution of the activity coming in. Okay. So this is the negative of the net gain. Okay, and then you continue moving to the right, and you see a vector in green that I have called y. That is the vector of dual values. So it's an interesting thing. You find the vector dual values there, and there is a dual value for each constraint in the problem. So you have m constraints, then you have to have m dual values. And since the first matrix, the small identity matrix, was m by m, then now here the inverse, which is in the same space, has to be m by m too. So you have on top of the inverse matrix, you have the vector of dual values, and to the right you have the values of the basic variables. Okay. The number of basic variables is equal to the number of constraints. The number of dual values is equal to the number of constraints, because there is a dual value for each constraint. So those two green vectors, the horizontal one and the vertical one, both of them have dimension m entries. This should be crystal clear to all of you. I hope it is. Is it crystal clear to all of you? Raise your hand. It can be. I asked one of the UT guys the other day, because I mentioned that this should be crystal clear, and the kid, so I asked him, tell me what you think. He sent me an email and he said, I was impressed. I think he used Google to translate the thing. He said, Professor Garcia, está tan claro como el cristal. He said, it is as clear as crystal. The guy said, crystal clear. He said, I saw, nice try, but good one. So if I don't want to cramp with your style, you are forced to comparing clarity to crystal, that's fine with me. Even though where I come from, we compare clarity to water. And I think both comparisons are fitting. And so I don't have problem with either one. But you can say más claro que el agua, or you can say crystal clear, but you need to send me your feedback. Any language you want to use, that's fine with me. But you got to send the thing. And you want to practice a little bit the learning of a foreign language, then try to do it in Spanish, and you have a little mistake, I don't mind. I know what you mean. Okay, so look at the table. On where we have AJ, now you have alpha sub j. The purple column at the beginning was AJ, now it is alpha sub j. And where we had see here, you can see both there, look. Where you used to have I, now you have B inverse. Where you used to have AJ, now you have alpha sub j. Where you used to have lowercase b face, or boldface, lowercase b, now you have x sub b. Okay. And where you used to have minus cj, now you have zj minus cj. And where you have the zero at the beginning, I have the zeros on top and the b to the right. I colored them in blue, but I could have colored them in green. Maybe I should recolor them, but at that time I didn't know it. I wasn't talking about dual values yet, so I colored them in blue, but it's the same.
What does the I stand for? It
See,
looks like
just
it holds
let
the
me
slate
get,
variables.
yeah. Which one here?
I, in your, well, it looks brown to me, I guess it's purple on yours. What does that stand for?
AJ?
No, I.
Right here.
I, the big one?
Yes,
It's an identity matrix.
okay,
Yeah.
thank you.
The inverse of an identity matrix is an identity matrix too. So it's always a B inverse, but the initial B inverse is an identity matrix. think about it. The small I here, this is square. And you put this on top and add this thing on the left. You consolidate the whole thing, you have an identity matrix, pick one. So it will be M plus 1 by M plus 1. The small one will be M plus M by M. So M plus 1 by M plus 1, or M by M, that's the small one. Raise your hand if this is crystal clear to you. Okay? I haven't registered this saying I have a line. I'm not going to register, not just yet. But the line goes like this, applies to all of you, to me too. See, we're learning things. And once you learn these things, you can play with these things. Once you learn the things, you can play with them. But if you don't learn the things, this is my line, the things will play with you. I haven't registered yet, but I have taught that to the UT kids too, over there. So I'm going to ask you to repeat it. Okay, it goes like this. If you don't play with these things, and the next thing is these things will play with you. So I'm going to say the beginning, and you say the rest. I'm going to say the whole thing first. If you don't play with these things will play with you. If you don't play with these things will play with you. If you don't play with these things will play with you. See, my mind is very clear, so I can say it effortlessly. Now, here you go. If you don't play these things, go ahead.
These things will play with you.
That's true. Don't forget that. That's my line. So you need to get to the point where you always play with things. We are here to play with things. We are not here so that things will play with us. Okay, we got this one, but I want to show you some things that are really important too. Let's see here. Okay, we talked about this last time, but I want to reiterate this. There is a vector that is called CB. CB is the vector formed with objective function coefficients for the basic variables. That capital B stands for basic. So C sub B is the vector of objective function coefficients for the basic variables. Now the basic variables are in this box here. That's what the basic variables are. So very important thing. You want this goes without saying, but it's good to say it. Look, you have the order of the basic variables is in here and in here. And there is always one that comes in and one that goes out. So every iteration has a list of basic variables that has been modified by taking one in and one out. Okay. So therefore, CB also changes from iteration to iteration. This is the CB0 is the coefficients, the vector coefficients for these variables. And CB is the vector coefficient for this variable. Very important things, if the variables are in a particular order in this box, because you may have something like, for example, x2 and x3 and x7, x2, x3 and x7, for example, 2, 3, 7. Then the vector of coefficients of the objective function have to be written in the same order. X2, X3, and X7. Otherwise, the whole thing is crazy. It doesn't make sense at all. So remember, you need to have them in the same order. Be consistent. So this is CB. Let's go back to that one. C is the raw vector form with objective function coefficients of basic variables xb, and B is the basis matrix. And that basis matrix formed with AJs, but they are put in the same order as the basic variables are in XB. In the other case, if you have 357 or 537, for example, 537, then it will be A5, then A3, and then A7. And that would be a square matrix. So if I say A5, A3, and A7, and I have only 3, it's because it will be 3 by 3. So for example, if I say what a basic matrix is formed with the vectors A5, A3, and A7, I say, well, how many basic variables do we have? Then you have to say 3, because 3 by 3 it gives you a square. So you cannot have, you have 3 basic, you have to have a square. You cannot have 3 basic variables and 3 vectors and expect to have something like a rectangle. Well, you get always a square. Think about it. Keep that in mind. So the basis matrix is formed with the AJ vectors of the basic variables. Now these are the very important properties. Let's put it like this. These are things to play with, okay? Because if you don't play with these things, then these things,
Play with you.
that's true. Okay, so these are to play with. Okay, the first one is y equal to CB inverse. I proved this in my reading guide, and in the book they are proved. So I'm describing them to you. Okay.
Are these the just to verify?
Okay. Now, well, these are just mathematical proof, but
Right.
there is an association between these and the tabular form of the simplex method, and that's where I'm going to tell you how you can find these elements.
Okay.
Well, you don't have the tabular form of the simplex method to actually use this,
Okay.
but the tabular form of the simplex method will avoid using this. It's important for you to see where they are.
Okay.
Okay. So the first one is CB equal to B inverse. Okay. Second property is ZJ minus CJ, that's the top row, is equal to Y, the same Y that we just found here, yeah, times the original column for X, because this is for XJ, look, ZJ minus CJ. So the vector dual values times the original column for AJ minus the original coefficient of xj in the objective function, okay, that will give the value that we have in the simplex method at every iteration on the top row. And if we are interested in finding the vectors, yeah, see, this vector AJ from this one, then what you need to do is to look at this one here, to your right, this one, and then multiply by this one. This times this will give you this. That's the way it works, okay? And so here you can see it. So that there are 3 properties. CB inverse for Y, then Zj minus Cj is equal to Yaj minus Cj, and the third property is alpha j B inverse equal to Aj, and here I have to the right something that we proved, is that the values of the basic variables they form a vector which is equal to B inverse times B. So it's this one here. Times this. So everything that you have here is equal to this times this, always. And when you have this thing, this, look, this vector here, you will be able to find it, but that is the result of doing this CBB inverse. You will get it. Yeah. So how do you get it? Then at any iteration, here, at any iteration, you need to check this here first. Say, okay, I have this basic variable. Then you go to the objective function and form the vector coefficient, the raw vector of the coefficients of this in the objective function. That's CB. And then once you have CB, which is a raw vector multiplied by this, and you get this. Well, the simplex, tabular form, the simplex, will give it to you directly. Okay, so here. Let's see, look at this. That is what I was trying to show before. Look at that. Okay, let's see. I have an illustration. This is can we focus this better, or I think it can be focused a little bit better. I know that my eyes are not that good, but not that bad either. Okay. Thank you. I have this illustration here. You have, you already know how to do it, but you have the canonical form for the primal, and then this is the corresponding dual formulation. Primal, dual. Okay, I'm going to solve the primal. So here you have, and I use the same colors, more or less, but this is red. Definitely this is purple. This is red, pink. And these are the non-basic variables, and these are the basic variables. Okay. When you look at your PowerPoint presentation with the computer, you will see that I'm using the same colors. This is supposed to be yellow. Okay. Well, you can see it on my PowerPoint presentation. They are perfectly yellow. Okay, so we have this, and we can start the simplex method because I have not only a small identity matrix here, but I have the large one too. The large one, I have the 2, 0 here, and I have this column that is permanent. So I'm ready. And then you do this and this. Okay. Well, you know how to do it, or you are supposed to know how to do it. And you must know how to do it. You must know how to do it. You are not only supposed to know how to do it, but you must be able to do it. Okay, so here is the identity matrix, the one that you asked me, I. So I, and then now this is B inverse and this is B inverse. And this is the lowercase b, the vector B. Okay, and this is the solution at any other iteration. Okay. This is, we're not going to do it, but we have, they simply have done it for us. For us, you multiply this by b, by this you get this. Now you in this iteration you multiply this by this, you get this. Always. Here you have x3 and x4 first, and x2 and x4, and then x2 and x1. Okay, now this one is A1 and this is A2. This is alpha 1, alpha 2 in this iteration, and this is alpha 1, alpha 2 in the last iteration.
Dr. Garcia, so are you saying now with this table, we're not dividing row 1 or row 2 by a certain number to get it to 1, we can just inverse?
No, we have done that already.
Okay, but then the inverse, that comes out to be the same? Is that what you're saying?
Yes,
Okay.
yes, that's true. Yes. Just actually doing the mechanical, the tabular form, the simplex method, all you have to do is how to apply the rules that to get you get the pivot, you know what comes in, what gets out, you do the ratio test, you select the one that comes out, then that pivot must be equal to 1, then you divide by whatever value it is, now you have 1, and now you have to convert the column with the pivot into a column for the identity matrix, so all the, except the pivot, everything is 0, and that's through row operations, and when you do that, if you don't make math mistakes, 100% sure that you will get that. Yeah. Now you do what I said, multiply this by this, well, you will get 4 and 4, so you can verify things. Well, you already have the results. Okay. So here, let's look at one again here, and this, I'm putting them together more or less there. And this is the first one, and this is the second one. So let's work on that one. I'm gonna not really find them because I already know them, but I'm gonna verify the formulas. This is a verification process. So I know that y is CBB inverse. Okay, I'm gonna do it for the second iteration or first one if you want to. It's the one that we call 1 because the first one is iteration 0. That the initial iteration doesn't count really. So here this is just the initial iteration, which is preparing the whole thing for the simplex, and this is really iteration number 1. Well, let's look for that iteration. Okay, CB, B inverse. Okay, what is CB? CB is the vector of coefficients of the objective function, or in the objective function of the basic variables. Then you look at the box that has the basic variables. And here you have x2 and x4. Well, x2 has, in that order, x2 has a coefficient of 7 in the objective function. Here it is, look, this is the negative of the coefficient. So this 7 is this one. And the other one is x4. x4 is a slack variable, has a 0 here. So this 7 and 0 comes from the objective function. Raise your hand if you follow that part that I did. Okay.
Why didn't you use negative 7? Why'd you just use positive?
Because when you write the objective function, instead of saying z equals 6x1 plus 7x2, you write it like z minus 6x1 minus 7x2 equals 0. But the
so go back
coefficient
to-
of the objective function are not minus 6 and minus 7, they are 6 and 7.
Okay.
So the first way, the best way is to remember, you got to remember that the objective function coefficients are given in the first row, but with the sign change, switch. Okay. So you remember that. See, and then you start playing with the things, because otherwise these things will. Yeah, I've seen it many times. You know, they could play with you. It's like soccer. You know, and you are the ball, and then you get the kicks. When you are the kicker, the things get the kick. So it's up to you to be the ball or the kicker. But when you play soccer, I have played soccer for many years. When I was younger, it's a beautiful sport. No offense, second to none. And you, I hope that before it's time to go into this beautiful world, you will agree with me. But you have some time. But back to the thing. You really need to know your stuff. And when you know the stuff, the things become very simple. So why are things difficult? Many times things are difficult because we don't know them. But when you start knowing something, it doesn't matter how complex it seems to be, then it becomes easy. Okay, then this is CB. Now I need the inverse. If I'm working on the second tableau here, then I borrow the red box here, and I put it here, look, 1/3, 0, 1/3, and 1. I multiply this by this, and I get 7/3 and 0, and that's this. See, I'm verifying things, not calculating anything, verification. Now let's see how I get this -4/3, how I can verify that. So I am going to use this formula. Well, I'm going to use it for x1. So the formula is zj minus cj equal yaj minus cj. That's a general formula, but I want to verify that for x1. Then it becomes c1 here, z1 minus c1 equal to ya1 minus c1. See, I wrote it here again. Look, c1. Let's blow that up. You will see that there's a z there. Yeah. So here I have z1 minus c1. Okay. Is equal to y. Y is this one. Look, I put it over here. And a1 is the vector 2 and 2 because x1 has a 2 in the first constraint and 2 in the second constraint. So it's ya1 minus c1. The coefficient of x1 in the objective function is 6. So it's -6, and you get -4/3. And now let's get this. I want to get this 2/3 and 4/3. We're verifying that. Can do the same thing here. See, and the time that you start seeing all this very clear, you start liking this, and I promise you that sometimes you cannot help it, or you want to go back to this thing. Say, I want to check that again. And every time that you check it, you enjoy yourself. You know what I'm talking about? It's unstoppable once you start liking all this kind of stuff. Okay, so here alpha 1 for x1 is B inverse, so I borrow the same red box which I already had here and here, and I multiply by the vector of coefficients in the constraints, which is 2 and 2. So I use 2 and 2 again, and I multiply this by this. You know how to multiply this, and you get this, and that's it. Now here you see how everything goes. Take a look. So all this is a verification because see, later on I'm going to use these formulas like this, stuff like this, to actually get results. But we have to wait until topic 7, I believe it is, sensitivity analysis. Okay? So here it is what we had before. Same thing. And now I'm going to introduce a new term. The new term is complementary basic solutions. See, at any iteration, as you have seen, there is a y on top of the inverse matrix, and there is a column which we call xv to the right of the inverse matrix. So that any iteration, you go after the inverse matrix, the red one. You go after it doesn't matter how big the simplex tableau is, or small. Then you go over there and you check the inverse matrix, and the inverse matrix is always in the same position where you have I in the initial tableau, always in the same. And usually we put this at the end. I don't mean to be tricky, but I could put the columns of I dispersed. I could. Who said I cannot do that? And then if I ask you to get the inverse, then you have to look at those columns dispersed again and you put it together. Because when you know, you know. Doesn't matter. When you know this your stuff, nobody can trick you. We can trick only those who don't know. We are taking advantage of the fact that they don't know. It's like taking candy from a child, but nobody can take candy from us because we know. So if somebody goes and gets you candy, you hold the hand and say, "Wait a minute." Okay, we are going to call them complementary basic solutions. One is the dual values, set of dual values, and the other one is the set of basic variables for the primal. So on top is for the dual, to the right is for the primal. So complementary solutions are one solution from the dual and one solution from the primal. And the two have one thing that unites them, and they are the common value of the objective function. So one solution from the dual, one solution from the primal are said to be complementary if they have the same value of the objective function. And then we go back to something I said before, that linear programming problems don't come alone, they come in like coins. One side for the primal, one side for the dual, and the worth of the coin is the objective function value. So at the beginning we have a 0 here, and at any iteration we have a z there. So that's the common value. Okay, here is a picture that illustrates a little bit of what we are talking about. I think it's a good slide. Here we have the primal problem, and here I have the dual problem, primal and dual. In here, I have the primal here in standard form. Okay. And here, I have the dual in standard form. So these are the original ones, and this is in the standard form. These are slack variables, and these are surplus variables. All of them satisfy the non-negativity condition. Okay, that's one. That's the other one. It's in standard form. It's the same thing that I have here at the bottom. Okay. You can do this, all of you. Okay, let's solve the primal using the tabular form of the simplex method. So this is the initial solution. Well, let's find the complementary basic solutions. So when you are given a table of the simplex, a tabular form of the simplex, then always look if it is in the first iteration, look for the identity matrix. This is the red one. Look for the red box here. I have not colored in red. And find those that are on top of the matrix, those values on top of the matrix, and those which are to the right of the matrix. So you get 0, 0, that's y1 and y2. And of course, this is 12 and 8, which is for x3 equal 12, x4 equal 8. Okay, now we are going to find basic solutions. The basic solutions have 1, 2, 3, 4 entries, because a basic solution is a corner point enlarged, augmented to accommodate the slack or surplus variables. So you have two slack variables and 2 points, two coordinates for the corner points. Then you have x1 and x2 for the corner point, and x3 and x4 for the slack variables. So a basic solution for the problem has x1, x2, x3, and x4. Similarly, a basic solution, here you will see basic solution for the duo. We have y1 and y2 and y3 and y4. These are surplus variables. So the number of coordinates in either one of the two complementary solutions is the same. You cannot have 4 here and 5 here, or 3. It's always the same. Okay, in the first one, let's see what are the values. I said in the first one, x3 and x4 are basic variables. Then the values are 12 and 8. Look, 12 and 8. The ones that are missing are x1 and x2. x1 and x2 are non-basic. Everything is non-basic, always 0. So you put 0 and 0. Now for the other one, y1 and y2, those are the ones that always are on top of the matrix, always on top of the red, the inverse matrix. Or in the first iteration, that's an identity matrix. So you look at the top of this matrix, 0 and 0, then you put it here, look, 0 and 0. Notice that I have colored these in red, red and red, because I have colored them in red here. Red here and red here are red here and red there, to facilitate the following. Same color. Do it quickly here. If y1 and y2 are 0, put them here, please. y1 and y2 is 0 here. And y1 and y2, 0 there. Then solve for y3 and y4. What is y3? y3 is equal to -6, and y4 equal to -7. Okay? Those values are this, -6 and -7. Look. That's the way, this is a very important slide, because that's the way you recognize the complementary basic solutions in a simplex tableau. And those solutions have a common value of 0. You don't believe me? Let's check it. Get the objective function here. Set x1 equal to 0, x2 equal to 0. Then you say 0 and 0. x3 and x4, 12 and 8, doesn't matter, they have 0 coefficients. So the value of the objective function is 0, is this value. Let's look at the others, okay? y1 and y2 equal 0, okay, this is 0 and this is 0. And this is -6 and -7, it doesn't matter. The value is at 0. Notice one thing, I don't know if you already checked it, but I'm going to give you a 5-minute break in a minute. Here, this is feasible, 0, 0, 12, and 8. Now this is 0, 0, -6, and -7. Look at this here. So it's a violation of the non-negativity condition. So this is feasible. This is what? Infeasible, yeah. And that's what I have there.
No.
Infeasible. So, let's do this. Second one. Let's repeat the whole thing. Okay. X1, X2, X3, X4. Okay. This one, I'm going to blow it up so you can see it. Okay, get it from here. Okay, let's do it together. Start with one. X1. What is X1 equal to?
Zero.
What?
Zero.
0. X2, 4. X3,
Zero.
0. And X4, 4. Okay? So you have already the values of the basic solution for the problem. Now, for the other, what is Y1? Then you look at his. Y1, 7 over 3. Y2, and Y3, and Y4. And the common value is 28. Let's see that. And then here now, let's look at these two that we just found. Okay, so you have X1, X2, X3, and X4. Notice that these were in red because they're given in the box with the basic variables, the values of the basic variables. And these are in red because they were on top of the V inverse matrix, 7 over 3 and 0. But the other two can be found to be minus 4 over 3 and 0 from the top row. Always, if you want to, once you have the red ones, look, y1 equal 7 over 3, y2 equal to 0, then you can go to these equations and you said y1 equals 7 over 3. You put it in here and in here, and y2 is 0, so 0 and 0, and get y3 from here and y4 from there. You always get the same thing that you have here, so why bother? Minus 4 over 3 and 0. And this is before the break. What can you say about that one? If you have to say only one word to refer to the solution, what is the word that you would use? Optimal. That's the word, the best word. Out of the dictionary, you know, I don't know how many words you have in Webster's, for example. And if I give you a dictionary and say, okay, choose one of those words in the dictionary that will fit. There are a few that will fit, but nobody will beat the word optimal. Okay. So that solution is optimal, and when it's optimal, then you can try that one. Here, I'm going to show it to you. At the bottom, then you have x1, x2, they come from the optimal solution, 3 and 2. These are non-basic, though they become 0. And y1 and y2 are from the top, 2 and 1, and the others are from the left of the red ones, and they are 0 and 0. Now what can we say? Both are feasible. So when both are feasible, you always get the optimal solution. Let's take a 5-minute break, and now we'll continue with this.
I have no idea what this stupid thing right here is just that row.
That's like the one thing that I have the hardest time with, and that's like the most important thing that we have. Because I can't just go from this and